Cool. Sweet. Hello. Which was camera? That camera? Okay. Thank you for joining my talk. Sorry about the technical problems. I am Zanzi. Some of you know me. I work with Leif. That's our little non-profit for doing canonical programming. Today I will present a canonical bidirectional typing discipline using Polarised System L. And it occurred to me that people might not know what System L is, but you might know the mu bar tilde calculus, and that's just not a name for it. I just prefer without the Greek letters. So first, let me address the elephant in the room. So it's obviously saying that something is canonical requires a heavy burden of proof. So before we begin, I will, can you give me a timer? Yeah, I will explain what I mean by canonical. So normally when we talk about a typing discipline for a type system, there's trade-offs. So you have trade-offs between expressivity versus how much burden of annotations you want to put on the user. And so in this case, our expressivity, we have the full linear logic. We have the four connectives. We derive implication, co-implication. This discipline I present is extendable to polymorphism, but there are some subtle issues with actually implementing polymorphism in a dependent type language that stood in the way, but it works for that. Important thing is there are no choices. So once I tell you the recipe, and specifically the polarity and chirality of each connective, this will fully determine everything. And the only annotations we'll need are going to be on the shifts between checkable and statistical stuff. So we're going to have a lot of binders, and none of those binders will need annotations. And as you can see here, it's going to be applicable to calculate and system L. So if you're doing calculi and you want to get some insight into the type checker, just embed your connectives into system L and hopefully give you some interesting insight on. And finally, structure recursive. So to type check a term in this polarized system L, you just structurally recurse. You don't need unification, but also you don't need to introduce any extra syntax. So there's a good paper on type checking called by push value recently, which introduces splines, and we don't need to do it. We just all we have, everything is internal to the syntax. So that's what we'll do. And before we start, let's have a warm-up. Here we have this interesting function. And raise your hand if you know what this function does. Raise the hand. Okay, people. Okay. Anyone else? Anyone else? I mean, it's not a trick question. Not for you. So, okay. Raise your hand if you think this function does nothing. Okay. Yes. Everyone's yes. This is a doing thing. Well, I'll tell you what it does, and it's about to, what it does is it's going to break semantic.
What does goes to?
So if you probably a case, it does.
Yes. Okay. Interesting. Yes, that's a good point. Yes. So the types are misleading. Yes, that's a good observation. Yeah. So context for this, I was working on a DSL a few days ago. And it had some types, some base types, it had some base terms. And the semantics of types was tuples, pairs of types. And the semantics of terms was the product category. And wait, can you see? Yes. So here's our semantic terms. We take a term, source of target, and we put it into the product category. And the semantics of terms, as usual, is indexed by the semantics of types. Now, if you know me, you know I'm not a fan of green slime, and this is obviously green slime. However, I thought, well, this is standard. This is how you have type interpreter. Semantics of types, semantics of terms. Nothing is going to blow up, or will it? Things blow up immediately. So Idris doesn't accept this function because in our sem term here, we have a function there, and the output of this function is a pair, tuple. But Idris doesn't realize this. It's not able to pattern match on it because it's stuck in the computation. So that's a bit annoying because, well, if I say this prefers for compiler engineers for Idris, they immediately figure out some clever hacks and fixes. But the problem is the point of functional programming is that we can reason about the code denotation. And as a dentation model, this is a perfectly good model. So the fact that the compiler doesn't accept it, and the fact that I need to think about the low-level unifying details just to make this work kind of means that functional programming isn't reaching its potential. But here is a fun fact. Remember our function from earlier? Let's call it the cursed identity. Because when we put this identity function into our semantics, there is no type error. So if you think this function is equal to the identity, well, let's do a test. Let's replace it by the actual identity. The error is back. So the function is doing something. And that something is not captured by the semantics of Idris or semantics of Martin of type theory. Because, wait, yes, okay, so the problem with that is that, okay, if you set as the identity, and the type system for Idris agrees with you, because you can prove as the identity, and the semantics agrees with you, because you can do equational reasoning.
What does is mean?
We're not going to go that deep. We're not going to go that deep.
If you said the things, all of them say that this is the identity.
Yeah.
No. That's the point. That's what I think.
Is there some, so the point isn't what I think is means, but the point is what the type system thinks is equal, and what the semantics thinks is equal, and there is an equation theory that will say it's equal, but the unifier doesn't agree. The unifier accepts the cursed identity function, but it doesn't accept the identity function. So this means that there is a divergence between what you think your semantics of your purpose system is and what the unifier says. And to an extent, this means either you need to have a better unifier, which agrees with it, or you should statically restrict and prevent the use of functions in a way that actually breaks your unifier. Otherwise, what is going to happen? But there is a third way. In a polarized type system, we can actually give the type to that function. It is a conversion between a negative pair, which is defined by projections, and a positive pair, which is defined by pattern matching. And even though we can give it a more precise type, which is invisible in Idris, this so far doesn't explain why we're stuck in the first place. And the talk will hopefully clarify it. So, plan for the talk. We will introduce System L and show a few fragments of it, the positive, the negative, and the combined. I'll talk about bi-contextual typing, and then I'll present System L in a bidirectional way. So the very top level picture is type theory is based on sequent calculus versus natural deduction. In natural deduction, we have sequence which are many to one. We take a list of things or a list of types, 2 of them. And this has the usual interpretation in the manual closed category, where the column becomes a tensor or a Cartesian product. In sequent calculus, we have many-to-many morphisms. And the important thing is that the interpretation of the column on the left is a different tensor to the column on the right. And this is what makes us different to just string diagrams. In string diagrams, you have tensor left, tensor right. But this is a category with 2 model products, and they have the condition of linear distributivity, which is a thing, but not very important for this talk. And importantly, operationally, the intuition is that you have a process which takes a stack of inputs and outputs one of the many possible outputs. So this is conjunctive, and this is disjunctive. And the disjunction is closer to classical disjunction, so it can support backtracking, and it can support a notion of first-class exceptions. So that's the sequent calculus, but there is a problem. In natural deduction, our terms have a distinguished type. We have T is a type of A in the context, gamma. In sequent calculus, we have these many-to-many morphisms, but we lose the flexibility of having this kind of distinguished type. And as a programming language, it becomes too difficult to work with. However, System L or mu bar has an alternative representation, where instead of a single judgment for terms, we split it into 3. And we have, and this is what chirality is. So we have things which have a distinguished output. So we have gamma, in context gamma, we output T of type A, or something in context delta. Or we have a distinguished input. In the literature, they're called coterms, which is a terrible name because it's going to be co-values, co-terms, co-producer, consumers. So I call them consumers. And these take a thing with distinguished inputs. So this is gamma times E of type A and outputs one thing and not. And the important thing is the cut. The cut connects a consumer and a producer. So they have to match on a type, C of type A and expression of type A. And we smash it together. And if you know about optics, you might notice that this looks like a mixed optic, which is interesting, but we won't talk about this.
How do you read this indentation?
Oh, yeah. Yes.
You have your semicolons next to your elements of your sequence.
Yes, so this
The first
is.
two cases, and then the parameters of your kernel, you have that. And then suddenly you have your colon on the outside.
Oh, yeah.
See what I mean? Is that a meta notation for like some colon that's distributing through all the terms?
Yes, thank you. This would be more of a meta thing, and this is concatenation. So I would read this top bottom, and I would say that we have C of type A in context gamma and co-context delta. So comma is just times here, and then E of type A in context gamma prime with co-context delta prime. And then this is just meta notation for the cut. So you have a cut, and the point is that you concatenate the gammas on the left and the deltas on the right, and the thing in the middle disappears.
But there's 3 different judgment forms.
Yes.
And that, I think Ross meant meta notation, like the bottom one is shorthand for one of the other 2.
Oh, I see. So that's a good question. So the first 2, producers and consumers, are shorthand for the combined one. So they're shorthand for this. You can kind of forget the focus and always get back a unfocused one, which doesn't have a distinguished thing. But the bottom one is the 3rd type of judgment. It takes the first 2 and compose them together. So this 3rd judgment is always going to be a composition of the first 2, where this is the top one and the second one is that one.
Yeah, just like, is being a producer or a consumer also like a meta thing, or is there?
So it's a thing that's going to play a very important role in what we talk about. So yeah, so it's interesting that kind of, in some sense, this difference is a syntactic limitation, but the calculus was built around it.
Yeah, so I mean, I don't see the syntax is my issue.
Yes. Oh, I see.
Where on the left hand you have a sequence of typing judgments, on the right hand side you have a sequence of typing judgments. Yeah. But then, so if I have just any of those, I can either pattern match it to producer or consumer.
So yes, so this is a good point. We will have, well, there is a stoop here. So it's like this comma maybe is, I simplify the syntax a bit. Usually there's a stoop. So it says that in context gamma with a stoop that has. Okay. Okay, so actually that was a mistake. I was trying to be simpler. But yeah, there's a stoop there. And we will have the mu and mu bar binders, as I'll show now. They can go between them. So okay, notation will change. I'm using code now because typesetting was taking a while and I was rushing. But same information as before. So we have 3 mutually defined judgments. We have our cut, which takes a producer, 2 contexts, and distinguish type A, and a consumer will also distinguish type B, and then concatenate contexts. And importantly, the typing signature producers, consumers look the same, but this type here is actually a distinguished output, and this type of consumers is a distinguished input. So there's a chirality here that's not quite captured by the syntax. But in addition to variables, which are just singletons, we have our mu and mu tilde connectives, and these just interchange in short form. So mu binds a covariable and gives us a producer, and mu tilde binds a variable and gives us a consumer. Kind of similar to something forced from called by fish value. And let me just build up a few connectives in the system. So lambda function types. The introduction for lambda is similar to the lambda calculus, but now we can bind a variable, which is the input, and a covariable would be like the stack that will handle the output. An application takes a pair of a producer and consumer and creates essentially a handler where we have your input and some handler for the output. Strict pairs. These are the introduction familiar rule for pairs, which is linear.
Sorry, can you go back to app?
Yes. Yeah, you kind of you
Okay.
yeah, it's like a stack machine.
Yeah.
Yeah, and so these are strict pairs or positive pairs, where you deconstruct them using a pattern. So you have a command with two variables in the input context and you have a consumer that takes a tensor. We have sums. Producers are the usual left-right introductions. The consumer is like, again, half a case statement. It just describes that we bind two variables individually, and then a consumer that can handle both. And then records, or in callback push value, these are called lazy pairs. We call them negative pairs, but same principle. So start with the consumer because that's just the projections. And the producer looks a bit weird. This is a co-pattern. It binds a variable into commands and gives us a producer of a with a b. And par. So this calculus can encode par because we have multiple outputs. And to introduce par, again, is a producer which binds two output variables. And remember, these are disjunctive. So either A or B is true in a kind of classical sense. And then we have a producer that produces one or the other. And the consumer needs to have a continuation for both A and B, and then it can match par B. This is interesting, but we won't dwell too much on par, but we can do it. So, okay, the operational semantics of this guy is very, very simple. There's a lot of rules, but it's a lot less than lambda calculus, because every rule in the reduction comes in pairs. And to evaluate it, you either use substitution or co-substitution. Where substitution substitutes a variable in a command for a producer, and co-substitution substitutes a consumer for a covariable. And so you have lambda matches application, pair matches the eliminator for pair, injections match sum, projections match the co-pattern introducing projections, and par. A lot of things happening, but the most important thing is that the previous calculus is non-deterministic. Because the mu binder and the mu bar binder, the one that switch between consumers and producers, are fighting for control. If you don't specify a reduction strategy, at some point there will be a mismatch, like it's not confluent. So if you choose one or the other, you'll get a different result. So at first it seemed like a problem, but in the lambda calculus, we have the same problem, which is that you need a reduction strategy. If you just mix called by value and called by name, you will also get an unconfluent system. And we fix this the same way we fixed the lambda calculus. Either we modify operational semantics, or we do things statically and modify the syntax, which is what we will do. And this is known as focusing. Originally, it's a proof search technique, but we can use this to focus on either the producer judgment, splitting it into normal forms and not normal forms, or the consumer judgment, splitting the consumers. So, okay, System L, the focused subcalculus. So for now, restrict just to the two connectives, tensor and sum. And now our producers are split. We have values which are the normal forms, and they're the primitive producers. They are pairs, introduction, the left-right injections. If we had lambda here, it would also be here, but for reasons we won't have it here. And we have our kind of general producer. We have the embedding of a value into a general producer, and we have the mu binder. So that's the producers. And the consumers we cut down and only have the complex consumers. So the primitive consumers, like first and second projections, typically System L will include them, but I will not for future reasons. So all of our consumers have the shape of patterns. We have covariables, we have the new binder, and we have the pattern match for pair and the pattern match for sum. And because they're all shaped like patterns, I just renamed them patterns. So that's what patterns. And now we can look at this restricted operation semantics. So we now have the connectives, but importantly, our connectives are focused. So a term is always either mu or a value. And the values are matched to a pattern. So in this fragment, operational semantics happens by a cut between a value and a pattern. And mu just gives control to the consumers. So now, note redundancy. So the presentation I did is very austere. I didn't do lambda, and I didn't include projections. This is because I will introduce them in the other fragments. Normal system L will have everything here, but there's a reason we don't want to be redundant, which will become clear later. Okay, so what if we do the opposite and we focus on the consumers? So we split the consumer judgment, and we have this judgment called stacks, which are co-values. They're primitive consumers. So here we have our projections, and here we have the power handler. So these are like, values are like inert terms that just kind of, they're simple producers, and stacks are the inert consumers. And we match them to the negative producers, which is again, we're not looking at the primitive producers, we've seen it before. So we're just looking at the complex ones. We look at a co-pattern for par and a co-pattern for width. And because I've restricted what I consider a negative producer, I renamed them to co-patterns. And it might not be obvious immediately in what sense these guys are co-patterns. And okay, lambda second, ignore lambda. But they're called patterns because patterns bound variables on the left context, which were inputs. These guys bind variables in the output context. And you can see how in natural deduction, it's difficult to talk about co-patterns because we only have one output on the right. So we can never really talk about binding things on the right. So far so good? Yeah. Two split syntaxes. And the operational semantics, again, really simple. We are focusing on the stacks, and we always have a cut between a stack and a co-pattern. And this drives the computation in this fragment. So, okay. Now, both of these are very restricted calculi. And what we want to do is we want to combine them into a single one, because we have a calculus that captures call by value, and we have a calculus that captures call by name. And what happens if we smush them together? So here we introduce polarity, and we smush all the types together. So now our types are indexed by point, and we have, tensor, which is the positive pair, and sum, also positive. And we have power and width, which are negative. Okay, I forgot to say there's also the units for all of them, but they're simple, so I didn't include them. And we have negations. Two negations, one between positive negative and one negative positive. And functions are now derived. And that's one reason I didn't want to include them before, is that I really like them to be derived, not primitive.
You have a decentralization at the bottom, you have twice S and type R. You find something possible there.
Yes. Yes. Sadly, there is no type checker for slides. But yes, when it says side, it means pause, and off means that. Okay. So, however, there's one complication. Once we introduce polarity, we can't type check the identity function, because as you've seen, functional types are defined between positive and negative polarities. And so now this doesn't check. So we introduce a thing called shifts, upshift and downshift. And essentially, to type the identity function, we just put a shift before, and now the client's match. And this is standard in polarized by push value, in polarized uncalculated, have the same thing. But it's actually going to become very important later, these shifts. Okay, so now let's look at the combined type. So first we'll look at the commands. So now they're indexed by kind, and so we have positive commands and negative commands. And positive commands are the thing from the positive language. It always takes a positive producer and a pattern. Negative commands always take a co-pattern and a negative consumer. And they give us that. So that's just a disjoint combination. And now we need to extend, we can combine all the judgments, and we need to extend them with negations and shifts. And I'll just quickly go through it. It might not be obvious, the subtleties of this yet, but it'll become important when we type check. So negation shifts between a stack and a value. And likewise, the other negation shifts between a value and a stack. So these are things that shift polarity, but they don't shift chirality. So, however, shifts change between a co-pattern, which remember is a negative producer, and a value. So it's and the value is a positive primitive producer. So we've done two things. We've shifted from positive to negative, but we've also shifted the primary chirality. Because in the world of co-patterns, the primary chirality is the stacks. Things are driven by consumers. In the world of values, the primary chirality is the producers. And this is the key point that will become very important later, but might seem abstract now. And the patterns, they have, well, similar, they're just the elimination forms for them. It's not like super enlightening yet. And the negative fragment does the same thing, but backwards. Values go into stacks, and the shift takes a pattern to a stack. Remember pattern, complex producer, stack, simple consumer. Now, you probably noticed all of these kinds, explicit kinds everywhere. We can actually collapse the 7 judgments we've seen so far into 4. This is the presentation of System L that I personally use. So commands are now cut between something of type with kind K, and I call them expressions and patterns, because so patterns are patterns and co-patterns, and expressions are the complex producers consumers. And expressions can be focused into values, and now values assume both positive values and stacks, which are negative values. And to make this work, if you know System L, you might notice that I had to do a clever trick, because collapsing values and stacks is straightforward because they don't have binding forms. So they are literally syntactically identical. But collapsing patterns and co-patterns is obvious because patterns bind a variable in the left context and co-patterns bind a variable in the right context. So to smoosh them into one judgment, I had to flip the context a bit. So this is different than the standard way. The standard way in the recent papers on System L is to use gradings and annotate the variables with producer-consumer grading and have only one context. And I didn't do this because the type checking algorithm I will show you will actually heavily rely on the shape of these contexts. So actually, they need to be split. So it says here, we want to have duality between. So just to reiterate, standard presentation of System L, the left context has both positive and negative producer variables, and the right context has the consumer variables. In my presentation, the left context has values and stacks, so positive and negative primitives, and the right context has patterns and co-patterns. And this will be very nice once I introduce bidirectional type checking. We have a lot of people who are experts on this, but just in case someone isn't very familiar, spend a few minutes on it. So bidirectional type checking splits terms into checkable and synthesizable. And traditionally, introduction forms are checkable, elimination forms are synthesizable. And this simplifies type checking. You can write a very nice structured recursive type checker very often. And you don't need unification unless you want it, because you can just annotate everywhere that you'd normally use unification, and then you don't need it. And actually, this fact was a motivation for this research work, because I don't like writing unifiers. And I was really trying to see how far I can push type checking without unification, and it turns out very, very far. So here suddenly we have good notation, and that's because I took it from Lucas's famous paper. So I have type checking. And so again, just to quickly recap bidirectional type checking, we have lambda. Lambdas usually are checkable. So the idea is that you have your context, you're checking the types, you reach the lambda binder, you know that you're checking it against the function, which allows you to make an assumption of what the thing in the binder should be, and continue checking. And applications are synthesizable. So the idea is that you'll see an application of some function to a value, and you can synthesize the body, and then you can check the argument against it, and it lets you synthesize the whole. And the important thing is the shifts. When you shift from checkable to synthesizable, that's not too bad. But when you shift from synthesizable to checkable, your synthesizing type needs to find the type, and your checkable type term needs to be checked against something, and you can't give it because you're synthesizing it. And so this is where you need to produce an annotation to get things and stuff. So that's the standard thing. Hopefully I didn't butcher it. Now, co-contextual type checking, originally an algorithm made by Noam Zilberger, which was based on backwards typing for linear languages. And that addresses a problem, which is that in the lambda calculus, the main binding form is a lambda, and that's checkable. And it's easy to check types under binders because you have a type to check them against. Problem is, if you have more complicated elimination forms, such as more complicated binders like pattern matching, and we've seen before, most of our elimination forms are very complicated, you can't go and you can make an assumption of the binder. Because if you're synthesizing a pair and you have a pattern match that needs to know what the two things are, you can't give it because you're synthesizing it. So the clever thing no one figured out is that you do things co-contextually. So instead of giving a list of types and a type that your type checker checks your term against, you give the list of variable names, which are untyped, and the output type. And what happens is that because you don't need types in your context anymore, you just pass the variables, and you keep going to the leaves. And when you get to the leaves, you see the variables. And normally variables are synthesizable because you get to the variable, and you look in the context, and you say, this is the type of this variable. Here, you get to the variable, and it's linear, so it's a singleton, and you're checking it. So you have this type you're checking against, and you look at the variable, and the variable has no information. So how do you check that this variable has this type? Well, you just split it. You just say it has this type. I've assigned it. And so this lets you type check things bottom up. It means that as long as your leaves are singletons, you can type check things co-contextually. So you might notice that this thing looks like a cut. This looks like a pattern. This looks like a value. And so you might notice that this is makes very convenient for us to type check the Sequent calculus. However, the Sequent calculus has two contexts. So we need to introduce bi-contextual type. So the left context for patterns is type check as I just described. The right context, we need to type check normally, which I'll show this in a bit, just give you the high level idea. But essentially, our normal context is typed co-contextually, our co-context is typed contextually. So I didn't make this terminology, that's just what it ends up as. But yes, the point is left context one way, right context the other way. Now, the last part was a bit abstract, so let me just clarify by actually showing you the type system. And you know, we started a bit late, and I spent a good amount of time introducing the background. And I think a lot of people here might not really care about System L so much as they care about the claim that there is some notion of a canonical bidirectional type checker. And so this is the part you may be waiting for. And you might even be looking at the clock, thinking, we have only a very small amount of type left, and we have a lot of connectives. And we'll actually deliver on the promise of showing you this canonical bidirectional type system. So I already have. So remember at the start of this talk, I said that every connective checking or synthesizing discipline is determined by a combination of its polarity and its chirality. And I've carefully introduced a calculus with no redundancy, where every single connective has a canonical place where it lives. And that's it. So just to kind of unpack this, if you look at a positive cut, as I mentioned, it's a cut between a producer and a pattern. As we've seen from the bidirectional typing discipline, or co-contextual, patterns are synthesized, and producers are checked against the pattern. So if you have a cut in a positive fragment, you synthesize the pattern, you check the producer. We're done. The negative fragment follows by duality.
Does this mean that the two hypotheses of this rule are written the wrong way around? They should flow left to right, right?
Oh yeah.
The rule should go left.
Oh yeah. Yes. I mean, yes, it's valid. Yes. It's usually when you write a program against a pattern, it's easier to write on the right. But yes.
Yeah.
Right, and the dual, the negative fragment, is a cut between a co-pattern and a primitive consumer. Now, co-patterns are synthesizable, and primitive consumers are checkable in this. And then you notice this where we diverge from the usual bidirectional wisdom, because that treats all elimination forms as synthesizable. But here we're saying the primitive forms are checkable, and that's because we're checking them against co-patterns. And this gives us a very nice way to implement type checking for co-patterns and code data for free. So this flows dually. And however, I haven't mentioned the shifts. In bidirectional type checking, we have the shift, synthesizable checkable. And you might think that we should put them on the mu and mu2 dividers, but we do not. Because even though they shift chirality, that's accounted for in a type checking problem. So yeah, it just works. That's not a problem. But what happens once we combine the two calculi together? So each of the connectives from the subcalculus retains the typal checkable discipline, and we need to add negation and we need to add the shifts. So negation switches polarity without changing chirality. So remember, negation embeds positive values into negative values and negative values into positive values. And because the primitives are always checkable, switching polarity to primitive doesn't change the fact it's checkable. And same way for the patterns. That doesn't change the complexity. However, shifts switch polarity and what I call the principal chirality. And this is the key idea, that there is a duality between the simple stuff that we focus on and the patterns or pro-patterns consuming it. And in the positive fragment, the principal chirality is the producers. And in the negative fragment, the principal chirality is the consumers. And what the shifts do is they shift between them. The left shift embeds a co-pattern into a value, and the right shift embeds a pattern into a step. And connecting this to bidirectional type checking, a co-pattern is synthesizable, a value is checkable. A pattern is synthesizable, a stack is checkable. This is the embedding of a synthesizable thing into a checkable thing. And that's not too hard, that's straightforward, the same as in the empty calculus. But the difficult direction is this one. We embed a command with a bound, so the pattern matches for shifts in co-pattern match. It embeds a command with a bound, so the positive one embeds a command with a bound negative value into a pattern, and vice versa, a command with the covariable, which is positive in a co-pattern. And okay, that seems a bit abstract, but the point is that it's the same as embedding a synthesizable thing into a checkable thing. We need to synthesize these variables so we can check things the other direction. And wait, sorry, vice versa. The checkable thing is synthesizing. So we synthesize patterns and co-patterns, but we need to check this variable and co-variable, which means that if we build this type checking algorithm, this is exactly where the annotations will go. The synth to check annotation. And that's the last slide. So yeah, in other words, we have a type system, bidirectional typing discipline that covers full linear logic. It covers, I didn't say multiplication because it's derived. So we just type check it by type checking the individual bits. Same with co-implication. Didn't say anything about it because really difficult to get a tuition for it, but we have it. And now we can go back to the very start and look at why we are stuck. So, okay. Can we diagnose this using purely what we've learned from the stock? So when we have our function in the semantics, that's a computation. When we are here, we're trying to pattern match on a computation. As we know from the positive fragment, a pattern needs to be matched to a value, and that's what drives a computation. If we match to computation, we get stuck. However, in the negative fragment, right, where is the cursed idea? Okay. In the negative fragment, computation is driven by primitive consumers. So first and second are primitive consumers. They will always have your computation in stuck. So what we're doing here is we're saying, use the negative, the primitive consumers, first and second, to create a positive pair. And a positive pair is once again a value. It's a primitive, and we can pattern match it. And this is what causes the thing to get stuck. So this is not a cursed identity function, it's a repacking of a negative thing into a positive. Yeah, that's the talk.